Dear participants, we are at the last session for today, that is afternoon session of this AICT Training and Learning Atal Academy sponsored 1 week online faculty development program on photonics, active learning in optics and photonics, organized by Department of Physics, Electronics and Photonics of Rajarshi Shahu Mahavidyalaya, Latur, Maharashtra. On this occasion, to give us a detailed idea about the manufacturing process of optical fibers, we have a renowned industrialist, Dr. Pramod Watekar, sir. I welcome Pramod Watekar, sir, for this online faculty development program. Welcome, sir. I also welcome. Okay, sir. I also welcome all the dignitaries present over for this session. And now I request Dr. Ramakrishna Kadam, Associate Professor of Physics, to introduce today's guest. Dr. Ramakrishna Kadam, sir, please.
Thank you, sir. Good afternoon, everyone. I hope everyone is safe and fine during this pandemic situation. It is great honor for me to introduce and welcome the chief guest of this session, Dr. Pramod Watekar, sir. Dr. Pramod Watekar, sir, is currently working as a Chief Manager R&D in Sterlite Technologies Limited, Aurangabad. He is associated with design and development of optical fibers, optical fiber cables, fiber sensors, and recently with process optimization. He was an Indo-French IFC PAR Fellow, then Department of Atomic Energy Fellow, Brain Korea Fellow, and then Brain Pool Korea Fellow. He obtained his PhD from Indian Institute of Technology, Kharagpur in 2004. After that, till 2010, he was a research professor at GIST, South Korea. He also holds Executive MBA from Indian Institute of Management, Bangalore. Today, his faculty development program, organized by Rajarshi Shahu College, Latur, he is going to deliver a lecture on commercial manufacture of optical fibers. With this short introduction, I request to Dr. Pramod Watekar, sir, to share his knowledge and experiences with us. Thanks to Dr. Abhijit Yadav, sir, for giving me this opportunity, and thank you all. Thank you, sir.
Thank you, Kadam, sir.
Thank you, sir. Watekar, sir, please proceed.
Yes, sir. Okay. I'll just share
your screen and proceed.
Yes, sure. I think my screen is
yes,
to everybody, right?
It is perfectly fine. Perfectly fine.
Right. Before starting my talk, I would like to express my sincere thanks to Professor Yadav and Professor Kadam for introducing me with such big words. I'm currently working in Sterlite Technologies, and I have some experience in manufacturing optical fibers, and I also obtained experience in manufacturing cables when I was actually transferred to cable factory. And yeah, that's not my earlier field, but it was interesting there. In last year, I was actually at South Korea again, where associated with some sensors required for missile technologies. So there's some experience in sensors and all these fibers. I would like to share what I know with you. Of course, the time is 1.5 hours, right? It's too small. So what we'll do I will just give you flavor of how fibers are manufactured, because the field where I work, I will explain better. Other things are theoretical things we can find out anywhere. Okay. So welcome everybody, all participants. This is and thank to Rajesh Rao Mahavidyalaya for giving me and this opportunity to give a talk against the fantastic audience here. So let's start. As a practice, actually, before starting, corporate talk, we have to give small introduction of our company. So I will just take 5 minutes before we go on actually go to our topic. So we are Sterlite Technology Limited, and yeah, this is our transforming everyday living by delivering smarter networks. This is our tagline nowadays. Are later very different. That's because we are not just optical fiber company now, because we are now data centers, cloud, the cloud computing. So we are cloud computing company, we are software company, we are networking company. We generally do FTTH fiber to the network, but there is no Sterlite. We actually lease it to Geo or Vodafone. These guys. Most of the Geo and Vodafone optical fiber networks, they are made by Sterlite Technologies, and I'm proud to say that the fiber used there are designed by me and my team. Just why we are going for fiber and all these things. The reason is that optical industry is going for a very exponential growth. The reason is too much use of uh, digital media nowadays. Even after lockdown, it has increased tremendously because of classes and all things. These slides were prepared before lockdown. So whatever numbers are shown here, maybe now they are much more. But it tells us that we have double internet users are increasing, so devices needed more and more. We need more applications, and data need per consumer is also increasing. That is now 8.9 gigabits per month. Maybe now it's very high. Coming to again, what is latency on these things? We are now in 4G area, right? But we are slowly moving to 5G arena, and we are working on the optical fibers. Actually, fibers are ready for 5G arena. This lockdown has delayed its deployment in India. Maybe by December, companies Jio and Vodafone they have not stopped it. They have postponed their deployment of 5G. So our orders are also now little bit delayed, but it is not stopped. It is going on. So 5G deployment needs better I will not explain why what is 5G because it's coming, but it needs some special things such as very low attenuation. Not only that, latency. I mean, like now I am talking with you, and probably you are getting my voice after 1 second or 2 seconds. There is latency. There is a delay. In case of 5G, uh, and if you are going to use it for virtual reality, it should not be more than 1 millisecond. So you can get actual real things. It is possible with 5G. And in 5G, there is another thing is that antennas will be connected at each premises, each colony. It's not that it's somewhere nearby area. It's not like that. Nearby your house, the antenna, short, small antennas will be deployed, and each antenna will be connected with optical fibers. Okay, so specialty optical fibers. We are making those optical fibers. That will 5G is going to change your world as mobile has changed our living things. This 5G is going to dramatically change our livings. You will experience this soon. We have seen it in when I was in Korea. They actually went for 5.4. That was a campus demonstration. And in that 5G, you go and stand nearby, car gate opens and you come in the home. If you are, you're very hot, you're coming from very hot, and you're tired, so immediately air condition will give very cold air, and it's slowly it will go to normal. So something like that. Everything going to change soon. Okay. Now, don't ask me question how it will affect our villages and cities. Definitely is going to give that lot of barrier between village and cities, and maybe we'll discuss later on. This is not topic right now, but this is a 5G and we need optical fibers, and we are there. I will skip some slides. So what Sterlite is doing now? Sterlite has silicon. We have our own mines. We call it Vedanta. We are all mining industry. We make our silicon. We make our silicon tetrachloride. We make our glasses. From glasses, we make optical fibers. For optical fibers, we make cables, and then We also deploy those optical fiber cables for different companies, service companies such as Jio and Vodafone, Airtel, and we also provide software for integration. So we are everywhere. We are now just not optical fiber company, but we are there give the service. Recently, we are operating in, for example, optical fiber plant. We are in Aurangabad. We are in Chendra and Waluj. We have 4 plants in Silvassa where we make optical fiber cables. We have a plant in China near Shanghai where we make optical fibers. We have optical fiber cable plant in Italy. We call it Metallurgica, Italy. And we have one cable factory in Brazil to cater American market. We call it for Sterlite. And our cloud center is at UK, Sterlite Clouds. And recently, we also acquired one now network connecting company from UK. So we are expanding a lot. Yeah, so there are global presence. We are everywhere, all over the world, and our actually 60% of our revenue from outside India. I'll just move forward. We have data center, edge networks. I will skip all these things. Some turnkey projects photos have been shown here. They are from Jammu and Kashmir. So our team were there to deploy optical fiber cables. We have telecom software, and yeah, we are now $8 billion company, and our target is to go for $50 billion in coming 3 to 4 years. That is, it is a little bit delayed because of short lockdown. All company machines were closed, and now we are struggling to make it on. So now it is going to be smooth soon, because once you are not operating the machines, they are machines, right? And then we have to now, it's a repairing phase. It's almost finished, and we are now into production phase. So it is picking up very large. We came into again profit this month because of huge orders and order realizations. As told, we have Silvassa plant, Italy, Metallurgica, the Italy plant. We have Aurangabad plant where we make optical fibers. We are in Brazil, optical fiber cables. We are in Haiban, China. So we're actually Indian multinational company. Yeah, so I will skip. Just will show where we are there. We are in Amazon forest. We have islands. We are deploying all in Himalayan range. Just follow and track race. So we have deployed actually optical fiber cable. So there is a huge experience there. I'll skip some slides. Yeah, thank you for this. Listening to corporate presentation. I will come to our topic now. Introduction to optical fiber manufacturing. As I told you earlier, I can give you, flavor of manufacturing because it's a huge topic. And in the some of topics I have actually worked, so I can elaborate this better. Some topics there which I not work. So I may not give details there. We can find out in theories and books. So my actually idea is to give you as much flavor, as much information possible, which is not available in books. So that is based on experience. I hope this session will be very interesting to you. Okay, so my topic is arranged this way. I'm not expecting any knowledge, even though you already covered optical fiber and a lot of classes there. So what is optical fiber? I will start with that, but not go into much details. And how to get optical fiber, how to make optical fiber, and then we'll go for, if you are going to make optical fiber, we need to make glasses. And then how can we make glasses? CVD, MCVD, OVD pad, sol gel, molten glass, and extrusion techniques. I will briefly give introduction of cables and we'll conclude there. And if you have any questions and answers, we can have that sessions. Or if you have questions, you can also send email to me offline. Discussion can be taken place. Okay, so coming to very quickly go to history of optical fibers. Long back, 1870. Yes. John Tyndall actually did some experiments with sunlight and water, and what to show that we can bend the light. It's not bend, light is always straight, because we imagine, we think fiber, light as a straight light, a ray, right? A ray is always straight. So he has demonstrated that this ray can be, bended. So we can bend this light. So he's shown this, put some water, and then the light was coming out of this spot. So we can bend the light. That is the reality. And if you use optical fibers, we can bend it anywhere. You can take the light and bend fiber, so light also bends. Okay. Quickly coming to optical fibers. Started in 1930s. There were used for transmitting images too, and that was not much work was done until the lasers were the first such lasers. Once you got lasers, the science send some images, and now that imagination now has turned out into this today's talk, right? I'm sitting here, you are sitting in your places, and we are talking to each other. So that imagination actually is turning into actual experience. So what is optical fiber? This is, I'm just explaining it so that it should be in continuation. So optical fiber has, as you know, we have core made of germanium, right, plus silicon. So silica plus germanium dioxide, its combination is core covered by cladding, that is SiO2. And you can coat it with polymers, whatever you like. So that is a simple structure of optical fiber, and mainly, as we understand, when you send light through this optical fiber, it takes shape of, it goes because of protein reflection, and it is because of array type things. And in actual practice, if you go much deeper into it, we can find that it is the electromagnetic field that is propagating to the optical fiber. But for our understanding, this is the ray that is going through the total interreflection, simple Snell's law, and all things. Right? This is how optical fiber works. It is very useful for communication. The importance of optical fiber is that it carries much more information. Right, it is a huge bandwidth. Right, so you can go for higher data rates. For example, in our laboratory, there is terabit transmission is going on. It takes a long time actually for commercialization, but we have to research on that. So the terabit company. So huge data can be transmitted. We are talking about gigabits per that type of thing, right? 5 GB, 10 GB, or what that. We're actually in terabits area, and sooner or later it's going to be commercialized. And the very important thing is that it's very light in weight, and it cannot be. It is immune from electromagnetic noise. I'll move forward quickly because we have to. Right. So we're coming to here now. So we know optical fiber, it carries light. It is made of SiO2 plus GO2 and covered by SiO2, then covered by polymers. And that's how we make optical fibers. Okay. So when we are deciding actually going for manufacturing optical fibers, we have to first think of what material we should. There are so many materials, right? So what is suitable material? And okay, so while want to choose the material there, we have to very first thing, most important thing is that what is the loss there? Okay? How much is the loss? And all our customers ask, what is the loss there? How much is the loss? For example, currently in books you must have read that it is 0.2 decibel per kilometer attenuation you get at 1550 nanometer. But that is very old, old number. Nobody will purchase 0.2. However, now we are going in now 0.185, 0.187, that type of attenuation is requested by customers. Okay, so loss is going down and down and down. It is 0.14 has been achieved by Corning's ultra low loss fibers. We have our own 0.18 and 0.16 fibers. So these losses are coming down. The demand. This is because when we deploy the optical fibers, we are sending light through it, and if you bend it, a lot of losses occurs, bending and these things. So to compensate that, people are asking, okay, you mean lower loss in the fiber, and then you have to work on that. So loss is a very important factor. So we should get minimum and minimum loss. Then that what happens there, nobody is bothering nowadays. Okay, loss. One more thing is that RI control. This is now coming to operations. I mean, you should have a refractive index of that in the fiber. We should be able to control it. We should be able to give some shape to it. If you want different properties from optical fiber, we have to control that refractive index. Yeah? In simple sense, refractive index is the resistance to the speed of light. More the refractive index, slower is the light. Okay. That's element terms. Yeah, and as I told you, shape control. Shape of refractive index should be controllable. If these three things can be controlled, then you can use that material. So let's see those materials are gas. Yeah, very simple thing. We have gas, liquid, and solid, right? So if you want to use gas, you can use them. Very low loss. Still, people use it, for sensing things. But problem is that the refractive index, along the length, it's very difficult to control. You cannot control it. Gas. It's gas, right? Its molecules are randomly moving from here to there. So gas based optical fiber, they are not much popular except for typical sensors. For example, I remember using gas type optical fibers in carbon dioxide lasers. They are very popular in carbon dioxide lasers. If you can sometime visit to what's that, Cat Indoor, so they have that CO2 laser. That is, but problem is it has a refractive index control. We cannot control. This is gas. The same thing can happen. But you can use it for some sending some lasers and those things. Then second things option comes. Okay, then I will use gas because I'm not going to use sensor everywhere. I want fiber for communication. Okay, then we can use for liquid. Yeah, liquid was successfully used for multi-mode step index fibers. For example, glycerin core optical fibers. I have seen liquid core optical fiber in South Korea also. One of my colleague was working on that. He was working on sensors, current sensors. So he made that liquid base. But what I see, we experienced that time. It's very difficult to put liquid in the core, right? We keep hollow core and then we insert liquid there. It's very difficult to push that liquid, right? So it can go up to meters, but we're talking about kilometers there. Very difficult. So huge difficulty if you want to deploy it, to make it, spoiling of that oil. So it was not liked by students. So not even it is not liked by the customers. So liquid based this optical fibers also become they are very specific application in sensing techniques. So they didn't become commercial. Right.
Sorry to interrupt. I think slides are not moving. Means participants are unable to see.
Okay, can you see now here?
Just unshare and stop share and then again share, sir.
Okay, okay. Oh, I miss, I think, right? A lot of things.
It will be better if you share desktop. So sometimes.
I have shared the desktop, I think.
Okay, okay, please,
sir. Suppose is it moving now?
No, it is not visible now. Please share once again.
Okay. Sure. I will just share here. Open share tray. Your entire screen, right? I'm sharing my entire screen. Is it visible now?
Yes, sir. It is visible now. Put it slideshow mode only.
Now is it moving or not? That's why I'm asking.
Solid state. It is visible.
Okay. Yeah.
You put it on the slideshow mode and you run it, so we will get idea.
Okay.
Then you scroll.
Right now scrolling. Gas, liquid.
No, it is not coming, sir. Now it came. Okay.
There's some delay, I think, right?
So small delay.
Right. Now it is solid state, is it?
Yes. Please continue, sir. Yes.
Okay. So, friends, were discussing on material, gas and liquid. We found that they are not so much useful commercially. So then we'll go for solid, right? Solid states. So we have crystals. If you want to use crystal, it's a beautiful thing. If you want to make fiber out of crystal is very difficult. How can we make draw fiber out of crystal? Crystal can be grown. So that is the problem there. Crystals can give very low loss, 0.1 decibel. Wow. So I will love that type of fiber, but we cannot make it. Kilometers, thousands of kilometers of crystal. How can we make? So there also, mass production is very difficult there. Then other instead of single crystal, we're trying to use polycrystals. Polycrystal we can go much bigger length. But what difficulty was observed that when you use polycrystals, there are grain boundaries, right? We have crystal boundaries. A huge loss. Use scattering. You send the light, it is scattered. So that loss actually prevented use of solid state materials for optical fibers. Then we come to glass. Is it visible now, this glass slide? I hope that everybody can
Yes,
see
sir.
the glass.
Yes.
Right. Okay. I will, after changing, I will stop some, so that
Yes,
everybody
yes.
gets
Small
some
pause. You can
line to
small
it.
pause.
All right, glass. This is my dearest topic, glasses, because glasses are very good. Very thing is that the glasses are not much lesser than single crystal, but there is no gain boundary type thing scattering. Scattering is there in glasses. You have material. This material have always some limitations. There are losses, but beauty of glass is that we can elongate it. Elongate it to very small dia. We can go for higher and higher length. So that's why glasses become very popular. Now, if you're talking about glasses, we have silica glass, chalco glasses. Chalco glass means sulfide glasses, telluride, selenites. We have fluoride glasses. So I have worked with silica glass and fluoride. We started work with chalcogen metal sulfide glasses, but it turned out to be very poisonous. We have to take a lot of care should be taken. Telluride, sulfide, selenites, they are highly poisonous stuffs. No, when there is poisonous, then it prevents its commercialization, isn't it? So its uses allow very limited chalco glasses. People are still using it for highly non-linear type of optical fiber manufacture. But chalco glasses are not much popular except that. And silica glasses become very popular because of low losses. Fluoride glass, we can have fluorine there. We use fluoride glasses. Silica plus fluoride, a beautiful combination, because silica plus fluorine can make the fiber bend insensitive. They are the backbone of FTTH technology, that is fiber to the home technology. Silica glasses, we use fluorine, trench there, fluorine and silica. Sometimes somebody will explain you in next classes. So we have bend insensitive optical fibers. So fluoride and silica, they are very successful, very popular type of materials. I will quickly move ahead. Why we are going for silica SiO2 cladding, and why GO2 core? Generally, we use SiO2 as cladding and SiO2 plus GO2 as the core. The reason is that GO2 plus SiO2 gives higher index, okay? And excuse me. Earlier, instead of germanium, titanium was also used. It was very popular, but that gives very high scattering. TiO2 gives very lot of scattering there. It is good. Loss can go up to 20 decibel per kilometer in very fantastic networks. But in our case, I found it can go up to 100 decibel per kilometer. It's very difficult to control titanium losses. So this titanium was, people dropped that idea. Germanium was very good. Losses were limited. It goes scattering there. Limited to 0.2, 0.35, something like that. So GO2 become very popular material. So we have now SiO2 cladding, GO2 core. So it is not pure GO2, GO2 plus SiO2, and germanium is very small at home. Okay, so now let's go to manufacturing now. I'm giving small introduction to manufacturing SiCl4. We in Sterlite we manufacture our own SiCl4. Okay, so I'll just give a glimpse of that thing. What is there? It is very simple process there. SiCl4 manufacturing. We have Si crystals coming to us from our factory, Vedanta, and in Africa. And we just pass chlorine glasses and heat it there, and we get SiCl4. It is very simple reaction, simple exothermic reaction, and it looks very simple, but main problem is uh, you know contamination. There is huge contamination there. We have to control it. If your SiCl4 is contaminated, then your optical fiber will have very high loss, very large loss. Okay. So we have achieved purity up to 99% in our SiCl4 plant. So that's why we use imported SiCl4 for core part. Core part is very small, right? It's 10. For example, in fiber it is 10 micron, while your total fiber die is 125 micron. So there is a tiny core part. In core part, we are using now imported because reducing it's possible to reduce this purity from 99% to 4959. But then there's huge investment. Okay, so we prefer to take import very few are that type of 39 or 49, 99.999 or 99.9999 purity of SiCl4. We use that type of things for core because light is going through core and surrounded by cladding. We can always use SiCl4, which is we need not spend that much expensive SiCl4 for cladding part, which is just for protection purpose. So we have SiCl4 manufacturing there. And just for your glimpse, if we have chromium ions, right? So if there is chromium, just 2 part per billion, or iron, it's 20 ppb part per billion. So just we have 20 ppb of iron can give 1 decibel per kilometer loss. See, 1 decibel per kilometer. We are talking about 0.2, 0.18 decibel per kilometer loss, and small contamination of 20 ppb is negligible, right? 20 ppb can give huge losses in optical fiber. So that's why containing this metallic contamination is very important there. Your contamination, you're going to spoil all optical fiber. You cannot save it. Nobody will going to purchase optical fiber. So there are methods to filter them out in SiCl4 manufacturing. I'm not going into much details of that. But yeah, but these plants are huge, and we always fear there going there because something happens. It's chemical plant, right? So yeah, like that. Now coming to hope that it is okay with everybody. So now we are moving towards glass manufacturing methods. Methods to manufacture glasses for optical fibers. There are several methods now. We can use any method. Even you can start manufacturing optical fiber glasses in your laboratory if you wish. Very simple is sol gel method. Many of you must be using that. Sol gel method. Then we have molten glass method. Melt the glass and then use the shape. This double crucible method, rod in cylinder method, chemical vapor deposition. There are many methods there. I work in the sol gel method. So those who are among the audience who has worked in that sol gel type of things, it's very easy to make sol gel. You take TOs, put water, and add some contents, whatever you need, and put for overnight, and you get the liquefied glass. Then you put it for drying for 1 week, and we get the glass. It's very easy to make. Problem is that it's very difficult to get the yield. There are so many cracks. You have to control those cracks. Right? So yield is very low. Most of things have to be thrown out. In lab, we use those parts for qualification or for characterization. That's a different thing. But to get yield from sol gel, it's very difficult. We can get it 15%, 20%, 30%. We can get that type of yield. And that's why it's very costly also. And it takes long time. We have to give sufficient time for that sol gel method to give the glass that we need. That's why sol gel method is, still people are using it, sol gel method to make tubes, okay, but it is not, we don't adopt it, sol gel method. It takes long time, and then we cannot compete with your competitors. Another one is molten glass and finishing method. It is also simple thing. You take precursors, whatever needed to make the glass, right? You take those things, take SiO2, put GO2 or whatever you want. Okay, put aluminum oxides. You put together and heat them, okay, at 13, 14, 1700 for if it is SiO2. Go up to high temperature, you get molten glasses. and then you pour it and keep it for cooling. It's very good. It is very simple and it's very easy to make glasses that way. Molten glasses. There is one check here where molten glasses it's very easy to get contaminated. In environmental, we have to pour it in from one pot to another pot. There are a lot of places where it can get contaminated. So molten glasses generally have very large uh, attenuation, but still they are very popular in making your window glasses. Yeah? So window glasses are molten. They don't use very expensive methods. But to make optical fibers, and we need low loss uh, material, and so molten glasses are not that much popular. But some companies still make molten glasses. However, rod in cylinder method is very popular, very useful, right? So we're actually using it for making what you call bend insensitive optical fibers. We'll discuss this soon. Then we have chemical vapor depositions. These are very popular. MCVD, CVD, chemical vapor deposition, modified chemical vapor deposition, then OVD, outside vapor deposition, axial vapor deposition. We had there are the new techniques there. We move forward. I will just quickly show you double crucible. It's simple. It's very thing. We have you take pots, right? You take pots, and then pour the molten glass there, and you can make it. It's very easy, as shown in this picture. If you can see the picture. There is one pot, then another inside there is another pot. You put the core melt here. You put another material here, SiO2, molten SiO2 here outside. Inside there is SiO2 plus GO2 materials. They're molten there, and this molten things comes out because of gravitation, and we can make the fiber. Okay, so there is a double crucible method. There is some experimental problem there because we have to maintain them in molten condition. So that creates really a nightmare for manufacturers. But they are used for step index and graded index, really multimode fibers. They're very good for multimode. I will move ahead. So double crucible method it's not used by companies nowadays. It generally is adopted in laboratories. They use that thing because it's cheaper and simpler. And in laboratories, we don't bother about much attenuation or things. For using that fiber for example, making lasers, we don't bother about that attenuation that much. So double crucible methods are used in laboratories nowadays. Nobody is using in optical fiber manufacturing plants. Another is a rod in tube method. This is a beautiful method. This is very good and expensive, but very good method because the rods are outside that silica, right? We know core and clad. There are two parts. So we take core rod separately. We take cladding rod, that tube separately. We put this core rod into the cladding tube and we heat it at the tip. If you heat it at the tip, it melts and comes down together. Everything comes out there, comes out at optimum conditions, and we get the optical fiber. It's very easy to go that way. So this is a very popular method. Only thing is that because you have to purchase, you have to make your cladding tube separately. That's another technology. You have to make core rod separate. That's another technology. So this process is much expensive, very very expensive. But still, it is used when fibers are expensive. For example, bend insensitive fibers. They are very expensive fibers. $25 per kilometer. That type of price for that one. So if there is $25 for just 1 kilometer, and if you are selling in thousands of kilometers, lakhs of kilometers, then in that case we can invest a little bit in this rod in tube method. We also call a RIC method, rod in cylinder method, rod in tube or rod in cylinder. In our company we call it a rod in cylinder method. This is very good method. It has very advantages that we can directly taking the core rod, right? We can make core rod, we can put in the cladding tube. So things are not much complex here. Okay, that is your rod in cylinder or rod in tube method. I'm going forward. Then we have chemical vapor deposition. Now, as I told you, this earlier method, sol gel was difficult to get intact glasses. There are a lot of cracks there because there is water is coming out and generates cracks. And then we have to adjust pH and a lot of things are there. And then we have seen most popular is a rod in cylinder or rod in tube method, which was very expensive. because there are different materials. So people always commercial manufacturers, they look for cost-effective method to manufacture optical fibers. So we have chemical vapor deposition. I will not go much into CVD because we'll go for modified chemical vapor deposition. So in CVD, what they I have seen this CVD machine was there in Guangzhou Institute of Science and Technology. When I was postdoc there. There was this CVD machine there, and when I went there last year, they sold it out. They sold it because of low yield and all those problems associated with it, and maintenance of white element. So it is not much useful for if you are going for optical fibers. There is because it has huge contamination there. You cannot control OH contamination, and more than that, growth speed is very slow. It takes long time. We need very fast, right? It's a very fast word. We have to sell it quickly. So if it's taking long time, then it is a very difficult situation. Its formula is chemical formula very simple. If you take SiH4, GH4, and oxygen, and you can get SiO2, GO2, and like that we can make core rod like that. But this is not, nobody uses it except laboratories. As I know, most of laboratories are now, this has become obsolete for them too. It's very difficult to make lasers and specialty glasses with this type of technique. I will skip this thing. Let me check whether this works or not here.
Yes, it is working, sir. Working.
Okay, can you hear that sound and everything?
Sound not audible.
Okay, all right. Okay, I will do this so that. Anyway, this slide actually, this video explains how OVD is used. It is very popular in electronic industry. We have walls here. There's vacuum chamber. We can put chemicals here. It's like that. It's very simple process, but I'll just move forward it. Right. So we give a lot of chemicals here, and they form the depositions. I'll stop it here. Then coming to the another method, that is modified chemical vapor deposition method. Right. This is modified, very popular now. MCVD, as you must have heard this name, MCVD technique. MCVD technique is even used by companies and laboratories and research industries. It is very good to make laser optical fiber for lasing application or highly non-linear optical fibers. It is very useful, but it is not much useful if you are going for very long distance optical fibers. This is because its yield is low. There is a limitation of the size, and making thousands of kilometer optical fiber in one go, it is not possible. We can make few hundred kilometers is possible with that, but it still uses very useful method, modified chemical vapor deposition method. What we do here is that we have SiCl4, GSL4, and you put different chemical there. Optical, POCl3, we call it Optical. So we pass this gas, we send O2 through this SiCl4 or GSL4, and when this O2 gas comes out of that SiCl4 part, which is called a bubbler, out of this bubbler, it takes the material with it, along with it, and we pass it to this. This is now a ready-made glass tube, so it forms a cladding. So we have glass tube here, we send this material here and heat it here. So if SiCl4 is going, oxygen is going, we are heating them from our side, it will form the SiO2, that deposition. So it is also simple. It's very easy to, we can control refractive index, we can give any shape. It is beautiful technique. Modified MCVD is a beautiful technique. I have used it extensively to make fibers for lasers and as well as for sensors. Because Korea's first optical fiber laser, it was 25 watts laser that does Guangzhou's team that I was part of that team. So we made that high power laser that time, and we use MCU technique. MCU is a beautiful technique. I love that technique, right? But we found because the rods are now 25 dia, or at the most you can go for 30, 40, 50 dia. You can compare with OD techniques, 100 dia, big rods are there. So that naturally the yield from, I mean, time needed to make optical fiber from MCUD is larger than other method, than compared to OVD techniques. Okay, outside vapor deposition technique that we are going to discuss. But this modified chemical vapor deposition is a very good method. There's a tube here. We send chemicals through it, heat from the outside, and it forms. If it is SiO2, it gets deposited here. GO2, and we can then do various combinations. We can play with it and make the optical fibers. I remember one instance is good to mention here. I remember when I was new there, they didn't allow me to, these Korean guys allow me to touch that MCVD machine. So I didn't know, these are totally automated, right? In IITs was very different. We had MCVD technique there. There was some MCVD technique. We used to repair it because there is no much funding. So we students used to repair it. Once it's okay, then we used to use that for our experiment. Once it is done, it will again go down somewhere sometime. Again we have to repair it. So we used to do like that way. And when these guys denied, no, you will do after training or something. This is good actually. We should take training and these things. But I was very desperate to use it, and then I operated it manually. So I remember that thing. I use it. I bypass all automations because I knew that So my friend and me, we just operated manually, and we made the first preform there. After that, they allowed me. That is interesting thing. Yeah. So MCVD is a very popular method, and when you hit it, it is high temperature. It is 2000 degree. So a lot of people use it still. So as there are bubblers here, I will just show one video that will be very clear to you. As you can see, this is the MCVD machine. It looks like lathe machine. Okay, we put tube here. It's a glass tube here, and we inside the glass we send our chemicals. And at high temperature, this is the burner here. At high temperature, you go on the glasses there. If you increase the high temperature, it makes glass. If you reduce the temperature, you can make the soot there. If it is a soot, you can put a lot of material in that soot to make, for example, erbium, and make the glazing glass. Okay, so this is the actual pathways modified MCVD technique. I'll just show one video here. So what you see here is that there are huge, so he is putting this fiber for drawing, okay? You can see they are the burners here. So we are generating a lot of high temperature, 2000 degree or 2300 degrees Celsius. And in that high temperature, we pass the chemicals. It's an automated thing. Yeah, hope that you don't have any questions here. So MCU technique is useful to make different fibers. As OFS guys, OFS is a good company in making sensing, sensors. So they use that technique to make sensing optical fibers. This is one of the photograph of using MCOD techniques. This is backside how they have controls here. I'm not putting any method because we had Sterlite also had MCOD system. Now it is converted to OVD. These guys are very intelligent, our Indian guys. It's just converted to another system. Very nice. Interesting. Okay, so as we discuss, in MCVD, it's a very good technique. The only problem is that if you are going for thousands of kilometers, it will take a long time. It's good for making hundreds of kilometers, very good for that. We are looking for thousands of kilometers. Then we have to look for bigger size of glasses, bigger diameter of glasses. Okay, so in case of this, we have now two techniques. We can axially deposit, or we can outside vapor deposition. Means we can deposit from outside. Both things are outside, but in axial deposition we go axially. It is, I will show one video so that it will be very clear to you. Yeah. So this is the OVD technique. So, right. Outside vapor deposition. This is very popular technique now. Number one company in the world is Corning. Corning glasses. You might be using Corning glasses everywhere. So Corning uses this OVD technique. They invented. They have that patent. Other guys use generalized OVD technique, modified OVD techniques as per their need. So if you go for outside vapor deposition, it's a very simple technique again. Same as MCVD. In MCVD, what was difference is that we have glass tubes, and in the glass tube, we are depositing inside that glass tube. We deposit the chemicals. I mean SiO2 and GO2. In here it is opposite things. We don't deposit inside the tube, but we deposit from outside. We take a mandrel, okay, graphite mandrel or something. We take, or sometimes we can take glass mandrel, and we have to remove that mandrel afterwards. So you take that mandrel. This is the central one is mandrel. Okay, this target rod. We say target rod, and over this we deposit the chemicals. Right. So SiO2, GO2, whatever we need, we deposit above this mandrel, and this mandrel is removed. So this is going to make you glass for you. So what we do initially is that we take the mandrel, and above that we deposit some layers at a low temperature. It is not very high temperature. It is something around 1500 degrees Celsius. So 1500 is not sufficient for SiCl4, SiO2 to make the glass. It needs very high temperature, more than 1700 degrees Celsius. So at lower temperature, if your temperature is lowered, what going to form with that soot? This ash type thing. Okay, this हमने देखा है ash. वैसे soot बन जाता है, yellow, white color. So we have soot here. This becomes soot, white soot. I will show one picture. It will be very clear to you. So we send our gases. There is a burner, and an interesting thing, we have burner. Through the burner, we send these gases. Okay, so heating and deposition is taking place at the same time. So we deposit such type of things. Then we take this soot, it's a big size soot, and put it in the furnace. We heat it again at 1700, and this soot now gets consolidated into glass because now heat temperature is very high. So slowly it becomes glass. Size reduces, and we get the glass. It is called as OVD glass. We use this OVD glass. So I will show you here how it is done. I think this is visible to you. Right side we can see there are white colored, some rods are there. These are called as soot rods. This is a soot. How it looks like? It is not glass. It is soot, white color, ash type. Okay, because temperature is low, so SiO2 is in particle form. Okay, micron particle, 5 micron, 4 micron, that type of. So we have micron particles. They become soot like these things. So we take this soot, then put in the furnace. It becomes glass. Now OVD is a two-step process. It's not a single step. It's a two-step process. What we do is that we, for example, we make the core first, then we make the cladding over that core. So it is two-step. Okay? We send SiCl, for example, we send SiCl4 to the burner. Remember, we are sending it through the burner, not from here and there. Okay? In MCVD, we are sending through into the tube. Here is, we are not sending into the tube because there is no tube at all. So what we do, we send this material through the burner. So burning plus reaction has to be taken place. That is, it's very important. This distance between this rod and your burner has to be very optimized. So we send material here. It forms a soot here. Once you get 100 dia of soot, we take it out. Okay? More than that, there is a danger of falling it down. Try कर सकते हैं. Nowadays we are going up to 150 in a new plant, but in old plants we still go up to 100 If you go more than that, what happens? There is always danger of breaking that this side rod, right? We call the manrail. It can break. So we take this is up to 20 kilo of weight. It's 20 kilo average. So this is 20 kilo soot. We take it out, and in plants we always use the term kilo. Don't use dia or something. So we take 20 kilo soot. Then we put it in the furnace, make the glass. Now it is very high dia of glass. Then we again from that glass we heat it again. We make it small dia and again put in the OVD machine, and over that we put the SiCl4, I mean SiO2 layer that forms cladding. So it is a two-step process. I hope that is clear to you. I will show one movie here so that you can understand how OVD is done. Sorry. Oh, sorry. You can see that we are heating, right? We are sending materials to the burner and its size is increasing. This is how we make soot, called a soot rod. So this soot will now become glass. And it's converted to glass now. Beautiful glass. Hope that is clear to everybody. Okay, so what we did, we take mandrel or initial glass rod over which we deposit the soot, okay, SiO2 soot, small particles of SiO2 of required dia. So generally we take, there are different companies have their own standards. So we use 100 thickness, that is 100 dia, and then that is called as soot rod. We take it, put in the furnace and heat it, and it becomes glass. So that way we make the core glass. This is core rod. Then over this core rod again we deposit another layer that becomes clad. So this is two-step process. This just I want to sintering. What is sintering? You're taking the soot rod, right? Soot. We have seen how soot is made. We take that soot rod and put inside the furnace, graphite furnace or any type of furnace you can use, and increase the temperature. So that process, and it converts that soot into glass. That process is called as sintering. Okay? So sintering is very important there. During sintering, what we do, we generally send helium and chlorine. Helium is useful to reduce bubbles. Chlorine is very useful to reduce oxygen, OH related losses. If you want to take out OH ions, water is everywhere, right? So we want to take out that OH, we must send Cl, and HCl is a gas, so it goes out. And our glass is free of water molecules, and that's why it is now we have our fiber nowadays. Recent latest fibers have very low or nearly very low. We call it near zero loss, and near to the level of scattering level of attenuation at 1383 nanometer. That is the OH water attenuation. It is very low. It is negligible attenuation at water level nowadays. Okay, so here are some photographs that we want to show. This is the soot here. Okay, we do the soot into the furnace. This is our furnace here, and so it's going inside. It's hitting here, sintering machine, and once it's this white rod becomes now transparent glass. We call it as a preform, sintered preform. So that is the step here. One more thing is degasification, because while converting that soot into glass, we are giving helium and chlorine. Chlorine will go out anyway. It's no harmful for our glass. But helium, if it is trapped there, it is possible that helium can get trapped. So if helium is trapped, it makes bubbles. So to avoid that thing, trapping of helium, so we are using helium actually to remove the bubbles. But it may be possible that it can use opposite cells. Generally, some trapping takes place at higher. I mean, if there are gaps like that, more than 500 micrometer, then helium can get trapped and can form the bubble. So degasification is done, which is just simple. We take that glass rod, heat at 1000 or 1050 degrees Celsius, and keep it there for 24 hours. We need to, then we get bubble-free glass. That is very important. Bubble-free glass. Not many bubbles are. If bubbles is there, if you are drawing at high temperature, that bubble will expand and breaks our glass. That's there. Okay, I think I can skip. Just I will show this what happens here, but we'll skip this. We need not go much details of this chemistry of this, how densification takes place. I will just show one picture here. Right, this is the picture of pores as I showed. Right, when we have soot, the soot, there are a lot of vacancies here. You can see this soot for naked eyes look very good, white colored soot, but if you go in micro, there are many gaps here, and it can trap the air or oxygen or helium or any gases. And if you are going to make what's called glass from this soot, this trapped air or trapped gas can form bubble. So bubble forming is a huge problem in glass industry. So to avoid this, what we do, we send helium there. Helium generally has tendency not to form bubble at up to 500 micrometer. This gap. I will show last picture here. Not go. When you heat it at in the furnace, after heating, it became very clear glass. It was like this way. Okay, there are huge gaps here. This is a soot here with many air gaps. Converts into very nice smooth glass here. Okay, bubble free glass. Still there we can see some bubbles here, but more or less it is very good glass. So this way we do sintering. Sintering is very important process in OVD. I'll skip some slides here. Why we are using helium and all things. The idea is that if you use helium, we can reduce the bubbles. Helium has the tendency not to make bubbles or come out if the pores are less than 500 micron. So helium, that is because of mobility. So that is what we have explained here. I will skip this slide. Then another problem, I'm actually introducing you to the problems we face. It's not just simple making glass and we are fibers. As I told you, there is first problem is making bubbles in the optical fiber in the glass. Second problem is OH. You say why OH is such a problematic situation? Why OH is a problem? OH is a problem because it increases attenuation at 1383 nanometer. And right, our operating wavelength for optoelectronics communication is 1550. It is very nearby. 1383 nanometer and 1550 nanometer. They are very nearby. So increase in OH loss, or we can say, this, if tail goes there, then 1550 loss also increases. That is problem. So then we must control this OH. And second thing, in case of FTTH, the 1383 also used for communication nearby. So 1310 nanometer is used for communication. 1310 nanometer, that wavelength. So it is very near to 1383. So we must control this OH. If there is OH or water molecule, then it will increase attenuation at 1383, and so it will increase attenuation at 1310 nanometer, which is used for FTTH communication. It also increase attenuation at 1550 if it is tails goes there. That is useful for long length communication, terrestrial communication. So this it's very important to control these OH ions in optical glasses. Otherwise, they will appear there. Okay, so what we do is that we do dehydration. Okay, we take glasses, hit 150, then gradually go increasing the temperature. That is called as dehydration. And we also give chlorine, as I explained earlier. We give chlorine treatment, chlorine and H2. Then that which form HCl. It takes out that hydrogen. There is large affinity there. So HCl means hydrogen gone, and we get oxygen. So in this way, we can remove the OH ions on the surface of those glasses, okay, or nearby surfaces. Okay, so this is what I want to tell you. What happened? Sorry for this. Is some change here. Okay. I am coming quickly to fiber drawing now. So is this fiber drawing visible to everybody? I think. Hello, sir. Hello.
Yes, sir. Yes, sir.
I see. Okay. Very good. Right. I'm confirming it because it should not happen that I am going talking and nobody is listening.
Yes. Yes.
Okay.
Yes.
So we are. I think that you understood. It's a very complex process, but I'm trying to make it simple. We make preforms, and now, so that's this glass we made OVD. It's called as preform. We take it to drawing tower and draw the fiber. It is for small video on that. Okay, and we will skip it anyway. I will explain myself. What is that? So we have what we take the preform here. This is a furnace, okay, graphite furnace. It can go up to 2000, 2300 degrees Celsius temperature. So we put this glass preform here because of temperature. You know, this tip initially this glass comes out slowly from top to bottom is coming like this way. It's pushed this way. So this tip get heated and it melts. Once it melts, it comes down. We collect that drop, cut it and pass it through the. So you can see the wheel is there. So we take this one and pass it through wheel and start to collect. We call it a spool. So it is rotating. So slowly we keep on hitting and keep on pulling the fiber. This is how fiber is made. Now while it is passing, we cover it with polymer. This is very necessary because if you use only glass fiber, it can make glass fiber, but it will break really quickly. We have nails, right? We have nails and all things. If you touch it there, it can break very quickly. It has tensile strength is very high, but compressively, it's very difficult to maintain that. It can generate crack and it will immediately breaks down. So we have to protect this fiber. This is glass. This is a small, 125 micron wire is coming through this. We call it fiber. So we coat it with monomer. Okay, Sterlite. We call it the Sterlite monomer, and then we put UV light there over this fiber. So there is a monomer, and then it is exposed to UV light. UV converts that monomer to polymer. Now polymer means your plastic. So it is covered with whatever plastic here, this like plastic, and we get beautiful optical fiber, which is now strengthful. There are a lot of tests has to be done. It's not just we cannot just sell like that way. So it should be very strong. It should not break. Okay? It should withstand up to 1 kilo of tension. That type of. We actually put 1 kilo of tension. We wind it with 1 kilo of tension, and we see it should not break. Then we also do tensile test. It should not break till 5 kilo of. We put 5 kilo, 6 kilo. We go on increasing that weight, the fiber, and you just see how it breaks, when it will break that way. Generally, it is 5 kilo, 5 to 6 kilo is the breaking weight for the optical fiber. So we take preform, we heat it, at the tip we get optical fiber, and then we test it. And then it is ready to sell. So this is actual optical fiber drawing tower. This is very big. It's maybe 15 meter or big towers. You can see there how optical fiber is coming. This fiber drawing, you can see the fiber is coming out of this. This is the fiber. Okay, this is your furnace, and fiber is coming out. And here, what we are doing the coating. I mean, polymer coating, Sterlite polymer. And this is how it will look from the top side. Okay, this is the furnace here, and your preform is going inside this furnace. So it is very high temperature process. You have to be very careful of safety and all things. And this is final product. Then we have fiber with core and clad, and then coating. Okay. We measure the refractive index. We see, okay, so everything is good. That is the fiber is the final product. One more thing we do is D2 soaking, deuterium soaking. You will be surprised what is this D2 soaking. As we have seen that we have already removed the OH ions, means water molecules, from the glass, so that it is free from water. So there is no addition 1383. But it is possible that when we are using that optical fiber for deployment, that hydrogen can, environment has hydrogen, right? Or in cable factory there is there are hydrocarbons. So hydrogen is there. Hydrogen can enter the fiber, and then there's your glass is full of oxygen. There is a lot of SiO2, GO2, right? There is full of oxygen. It can break the bond, and the hydrogen and oxygen can form OH. So even though we have taken precaution to avoid OH loss, it can be generated in subsequent processes of cable manufacture. To avoid that things, there is another thing that is called D2 soaking. It is simple thing is that this is I will quickly go through it. This is our amorphous glass. We have disordered structure, right? Crystalline means beautiful order. So this is amorphous here. It has no order, is distorted. So glass is our amorphous in nature. What happens is that the bond between this is Si, right? SiO, Si. This is the bond. This is chain, right? SiO, Si. That is the chain there. That bond can be broken. As I told you, hydrogen goes inside. It can attach to oxygen. It has high affinity, so it can break the bond. So we get OH here. So we are avoiding OH, but we can get OH because of cable manufacturing process. This is a huge problem in, for example, in power cables. We have power line cables. Nowadays, power line cables also use optical fibers for sensing temperature and something. So in that power lines, there is a huge, because this is a high temperature process. When they manufacture it, there is huge possibility of hydrogen escaping, and the hydrogen can enter the fiber and make OH loss. Okay, so to avoid these things, what we do, here. So what we do is, instead, if there are some bonds which are broken, okay, because fiber is amorphous, right? The glass is amorphous. It is not such a beautiful structure. There are a lot of defects there in the glass. So we always have broken oxygen SiO bonds. For example, we have Si and O. It may be broken here, right? So when we have such broken bonds, what we do, we put D2, deuterium there. So D2 makes bond with oxygen. So now these defects are no more left for hydrogen to occupy. So if hydrogen is generated in the subsequent process, it enters the fiber, but it has no place there to make bond, and so you will not get OH loss. So this is called as D2 soaking. D2, we always make D2 bonding. Now you may ask, okay, deuterium, if you are giving deuterium there, will it not increase the attenuation? Definitely, it increases the attenuation. DT increases the attenuation in optical fiber, but at very higher wavelength. For example, generally at 1900 nanometer, 1900 nanometer. So it is far away from our 1550 nanometer. 1382 is very nearby, but 1550 is very high, far away. So okay, if we are making attenuation at the wavelength where we are not using it for communication, it's okay. In future, maybe if people want to use that wavelength also, 1900 nanometer for communication, then that will be a problem. But right now, we have no problem. So we always put optical fiber for this deuterium. This is after manufacturing optical fiber. We must do this deuterium soaking. That avoids the next problem. Okay, I just skip some slides. Then once you have fiber, we are tested. So what we do cabling of optical fibers. We cannot use bare optical fibers. We must do some cabling. We must put coating to over it. So what generally is that we take the optical fiber, then we color it, because we are going to put many fibers there in the cable. Okay, maybe 100, 144, 1000, 10,000. So the huge density is needed by companies nowadays, just to avoid future deployment. Okay, so we so how can we distinguish different fibers? So we make group of fibers and give them colors, color codes. We give colors. We call it coloring. Blue, red, black, different colors are there. So there is a coloring, which is a very important process. We do coloring. Then we do buffering. Buffering means we putting fiber in the jackets. Some small buffer is there, tube is there. We put that fibers in that buffer tube. We call it buffer tube. It is just plastic tube, so that we can group those fibers. Then we stranding. Stranding means helically we putting this way, winding it. Instead of giving them straight, we little bit twist the fibers, twist those buffers. That advantage of polarization mode dispersion. You may discuss further. To avoid that polarization mode dispersion problem, we use do stranding. Stranding is nowadays it's not compulsory, but everybody use that thing to avoid polarization. Then there is jacketing, means you take this fiber, put it in the plastic tube, then take many such plastic tubes are taken together. Then we do jacketing. These are covered in under another high density plastic tube, HDPE tubes, and that is called as cable, niche cable. It looks like this way. There are your fibers. There may be gel or dry. Is covered with this plastic, small plastic tubes called as buffer tubes, okay? HDPE or high density polyethylene tubes, and then covered by another jacket. So this protects our optical fiber. We cannot use fiber like that way. So we have to use cabling. Cabling is a huge. It costs around 1 lakh per kilometer just for manufacture of these cables. Fibers are cheaper, but these are very expensive. Cables are very expensive. So when Jio or Vodafone, they are deploying, hundreds of kilometers, thousands of kilometers of fiber. So they have to spend a lot, huge. They are the fiber, and we have to take, while we make the cable, we have to take care that it should be rodent resistant. We have mice, rats, right? They can eat it. We have to put that poisons or rodent resistant things. Sometimes mesh of metallic mesh to avoid rodents, to avoid rodent cuts or mice or rat cuts. These are called as. This is how the fiber is made, okay? And the plastic tubes, buffer tubes, I told, they are called as loose tubes. So this is the structure of optical fiber cable that we use. Inside we can see there is a very strength material. We can use anything here. Central strength element. Generally FRP or steel is full. Generally FRP is very popular. It's low weight thing. Fiber reinforced plastic material that can be used as a central material. So this is how cable is made. And then we just making cable is not enough. We have cable, then we have to make duct there, right? They have to be when we deploy it inside the in the ground, we have to make a duct. So that is also made of just water pipes. So, we have seen the water pipes, Jain pipes. That is just duct. So in that duct, we put that cable. We can put many cables, one cable or many cable, and that duct can protect our cable again, okay, from rodents and from cutting, because we have a lot of diggings going on everywhere. So we have to do that that we can use. That's called as ducted cables. We can put cable directly, or we can put inside the duct. That's how deployment takes place. We need not go into the details of field ratio or things. Okay, I try to give you a glimpse of how fiber is manufactured using different techniques. I could not touch axial deposition technique. There's no much time here. But I think I work in OVD and MCVD and Sol Gel, so I give small flavor of those processes. Thank you very much for attending my lecture. I hope that you enjoyed it, although it is very off topic for you. If there are any questions or things, you can ask me, or you can offline we can discuss. Thank you very much, everybody, for attending.
Thank you, sir.
Yeah, thanks.
Dear participants, if you have any questions or queries, you can raise your hand or you can unmute yourself and you can ask directly question to the sir.
Right. Or you can visit our plant to see, right, sometime.
Yes. Dr. Bharti Patel, madam, please ask your question.
Sir, am I audible?
Yes, madam.
Sir, I wish to ask one question, that how you come to know that the fabricated fiber is perfect to use?
Please unshare your screen. Stop share.
Right. Hi, Dr. Bharti. It's good. Very nice question.
Hello.
Yeah.
Sir, thank you.
All right. It's a very good question actually. So what we do, we can't use. We are drawn the fiber, but we can't use it directly. So the part I skip is the test methods. So we make the fiber. Initially, what we can control during drawing is the dia. We always check it is automated. It should not exceed 125 plus minus 0.5 micrometer. That type of control has to be there. Okay, these are all standards given by ITUT, International Telecom Union. We have to follow those norms. Now, when you have this fiber, which is confined, which is just 125 micrometer dia, covered with 250. Total dia is 250 if we include the polymer. It's coating. So if we make that fiber, then we have to test. It should not break, right? We are using somebody who can pull the fiber. It should not break. So there is a break test. We call it PT test in our company. PT test, tension test. Okay. So we give actually 1 kilo of tension. That is a standard specified by ITUT. We have to follow that one. So we give that 1 kilo of tension and pull it. It should not break. Okay. So we wind that fiber. We cannot just use the fiber that is drawn. So we have to wind that way. Second thing, now to make it free from OH, we put it into the deuterium D2. So that OH is gone. Now still we cannot use it. After we get that fiber from D2 soaking instrument, then we have to test it now. We have to test everything. 100% tests are done for attenuation. Okay. Attenuation should be always less than average attenuation should be less than 0.2 is the norm, but it should be 0.19 decibel per kilometer for our industry. So we test the attenuation at different wavelengths. Okay. We check dispersion there. We check zero dispersion wavelength. There are various optical parameters. It must follow all those parameters. And if it passes in all those parameters, then it is packed. That goes for next section is called as packing. We pack it and then we sell it as $8 per kilometer.
Okay. Thank you, sir. Thank you, sir.
Welcome.
Thank you.
Good afternoon, sir.
Yeah, good afternoon.
Dr. Pramod Watekar, sir. Thank you very much. Your lecturing method is very interesting one.
Okay,
sir, for
thanks,
me, presently you are going to using which method? I mean, preparation of this one. Which method you are using? 1 point.
We use OVD technique, outside vapor deposition, right?
And
in China we have
MOVD is also using or not only OVD?
No. Currently we use two methods. In India we use outside vapor deposition. In Chinese plant we have axial vapor deposition.
And second question, that what about this Vedanta? Whether you are tied with some preparation or it is also one of the part?
Sterlite is mother of Vedanta.
Sterlite is mother of Vedanta.
So Vedanta started with Sterlite actually. Now it becomes so big that we become part of Vedanta. So basically Sterlite Technologies was Vedanta earlier.
And third one, sir, it is required, I think, related to equity related, whether you are a public sector or it is a private sector. Sterlite Technology.
Yeah, public available. The shares are available in the market, NSE and our.
Yes.
Yeah,
I know since from 10 years, but interestingly, I am asking to you regarding this.
Yes. Right. As I explained, I am not giving direct answer to this question, but I am giving one hint that we are going to expand our. Now we are $8 billion. Target is to go for $50 billion in next 4 years. So you can imagine what will happen there.
Yeah. Thank you, sir. Congratulations.
Welcome. Right.
Dr. Shehzad, please unmute yourself and ask question.
Good afternoon, sir.
Pramod sir, I'll share your screen, please.
Oh, okay, sure.
Am I audible?
Yeah. How to
Yes, sir.
share?
Am I audible,
Yeah,
sir?
yeah. Please ask. Please ask.
Sir, it was very nice session that how to make optical fiber and the manufacturing process.
Yeah, thanks.
Sir, I want to ask very silly questions. That means one is about the
No
core
question
and
is silly. Please
cladding.
ask. Please ask.
Yeah, core and cladding. What are the method to use to measure the thickness of that core 2 mm, 3 mm? This is my one question. And second one is in your one slide you have shown that chromium 2 parts per billion impurity.
Mhm.
How
Right.
you are measuring such a small things? What are the
Right.
process?
Right. So we're coming to the first part, how to measure that, diameter is very essential to have that type of equipment to measure. Generally, method is your laser-based diameter check, right? If we put the laser there, right? So we know predefined diameter is there. If your light crosses, there is interference. It will be different here. So your light, there is a laser beam, and your fiber is passing through it. Okay, suppose sides or something, and then it can be calibrated for the diameter. It's very sophisticated equipments we have to use. Okay, so laser-based diameter control equipments. Coming to second question, what was the second question? Is chromium, right? Go to PPB. So we have to use atomization equipments, the FTIR based measurements. We have to use those type of equipments to control chromiums. How we can remove that type of impurities in PPB level. There are various techniques you can. There are very standard. It's not a new thing. It's not rocket science. Chemical engineer guys know that type of thing. So we can always you can hit. For example, the one technique is you can go on hitting from top to bottom and bring all the this contaminations downwards. Such type of things are there. So we have those equipments there in SiCl4 plants to control those type of chromium. Now in fiber, this is the regarding SiCl4, but in fiber also we can introduce a lot of metals, right? So what we do in optical fiber plant is that we control this metal polish. For example, we have more machines which are made of metal, right? So sometimes this metallic particles, micro, because it's very high temperature, they can fall there, and they create catastrophe. Our fibers fail, huge fiber. There is a huge loss there. So we have to always suck them out. There is a sucking instrument. Suction is there. So we suck all. It's working 24 hours. It's continuously in that machine. It continuously suck the gases so that no particle is going into the glass. That care has to be taken. I hope I answered your question.
Yes, sir. Thank you, sir.
Thank you.
Dr. Devkate, please ask. Dr. Devkate, unmute yourself and ask your question.
Hello.
Hello, sir.
Hi,
You are
Dr. Devkate.
Hi. Yes, sir. I have one question. What is the theoretical lifetime of this optical fiber?
Okay. Actually,
Yes,
we
what is
calculate. Yeah,
Yes.
sure. Yeah, please go on. Is that the question? Okay. So question is what
Yes.
is the lifetime of this? So we have tested what we call as a viable model. We follow the viable model for determining the life of these optical fibers. So we do experiments where there are fits there. So we do what happens is we create cracks and see how much time it can withstand the cracks at exceeded load, extreme loads, right? And that is then overpolated to that some years, what will happen in the future. That type of predictions are there, models are there. So model predicts life of our fibers to be is about 25 years to 5 years. But in practice, the fibers which are till now deployed on the earth, right? They are still working from last 40 years.
Okay, good.
So as you know, America is not putting many new fibers because it's already they are already deployed much before ours. So old multimode and single mode fibers, they are still working very well. So people thought after 25 years we'll replace it, but they are working very well. they have not replaced it, and that's why they are lagging in new technologies, right? 5G and these things. You don't find America's name in those type of new technologies because their fiber they cannot support these new technologies. Now America is also going to deploy new cables. Okay. But yeah, life is very higher than theoretical one. Theoretical is 25 years, and practically it has been observed that they are still working after 40 years. 40. Thanks.
Oh, okay, sir. Thank you. Thank you very much.
Welcome.
Thank you, sir. Dr. Unda Raute, please ask your question. Raute, ma'am?
Hello, sir. Am I audible?
Yes.
Thank you, sir, for your very nice talk. You
Thanks.
have covered many practical aspects regarding optical fibers. I have one question. Just now you mentioned that we can visit your plant. So,
Yes.
how many students at a time are allowed to visit?
If you go in the batches, generally there are 40 students we can accommodate. At a time we can send 10 batch of 10 students. You can visit it, but not currently, not now. This is not a good time to visit because we are repairing our instruments because we are open after lockdown. So next year it can be done very well. Nice.
And with whom should we communicate? Can you share?
You can talk. You can just email to me. I will forward it to our HR.
Okay, sir. Thank you.
Welcome.
Dr. Bharti Patil, madam, one more question for you. Please.
Sir, my question is related to students' requirement. Sir, what is the minimum qualification or the skill that is required to get a job in your company?
Okay, actually, in our company, managers they are mostly PhDs and MTech and Bachelor of Engineering. But recently, we are also taking DETs, means diploma engineers. Instead of using operators, right? ITI operators, we started to take diploma engineers because they can take responsibility very well. So machine operators are now actually diploma engineers. Over them, we have engineers, masters or Bachelor of Engineering. Those students are there. And the managers are maybe MBA or maybe PhDs and MBAs for like us. We are scientific faculty, scientific managers. So there are pure management managers. So MBA guys, they are also there.
Okay.
If you want to enter R&D, then you have to be PhD from reputed institution. Generally, IITs and NITs are preferred.
Okay. Thank you, sir. Thank you.
You're welcome. Welcome, madam.
Dr. Piyush, sir.
Hello.
Ask you a question. Dr. Piyush,
Hello.
You are audible.
Hello.
You are audible, sir.
Yes, Dr. Piyush.
Sir, I have one. After doing a test, really cool, sir. Inside that letter, and how it joins, sir.
Dr. Piyush, we could not hear you. It is breaking your voice.
Actually, sir, I am asking that after preparing cladding, how you feel core inside that cladding, sir?
Okay.
Sir? What is
right,
the
very nice. Yeah, I will tell you. What we do, we first make core. We don't make cladding. We make core. And then we stretch it to fit into the, because we are going to make bigger rod, right? So we have to see the capacity of our machines. So what generally we do, I will tell our case because different companies have different dimensions. So we make this preform 100 mm dia, right? That is GO2 SiO2. Then we stretch it to 28 mm, 25 to 28 mm. So we make such a small dia. Now we take that 28 mm or 25 mm dia rod 1 meter, over which we again deposit only SiO2. That forms the cladding now.
Okay.
I hope I answered your question.
Yes, sir. Yes.
Thank you, Pramod sir, for this nice lecture. Now I request one of the participants, Professor Chandrasekhar Chikegowda from Government Degree College, Gulbarga, to propose vote of thanks.
Okay. Thank you very much for actually listening me quietly. It's very difficult topic actually. Manufacturing is a boring topic. But we'll meet again. There is second lecture for me as well. Tomorrow, right? Yes, we'll meet again.
Good evening, everybody. Especially Dr. Pramod Watekar sir. This our Rajashri Shah College is maintaining the time is very accurately. So as usual, we are attending so many FDPs. According to that, also today's the session is started at 2 o'clock, 2 o'clock 15 minutes. And Dr. Pramod Watekar sir has started that session is very interestingly because it is a lecture cum demonstration method, or else I can say it is a practically method, because slowly you are explained and the things are very clearly, very reasonably, the sound is also very clear. So your given lesson is very interesting one, and you are given since beginning starting to the end points, means you are started the methods different. You told me the different types of methods, that is sol gel method, double crucible methods, afterwards chemical vapor deposition, CVD, MCVD, and now at present you are using OVD, the same methods which we are using in our research methodology also. So you are now opting technology nowadays, new technology methods are also you are opting. That is the very good thing, one interesting one. And after that you are given yeah, I think we are expecting to get the 5G within a short period, or maybe in next year we can get the 5G. And you told me that word, I will repeat it, that the antennas are available or connected with optical fibers in each and every colony, because nowadays the Geo company is providing the Geo fiber nets in each and every, I think every colony is like that they are providing.
Yes,
so we expect as soon as we can get the 5G also. And coming to different types of methods, I think I am somewhat about worry about this gas fibers, very typical method using that one. So generally we studied and we heard the solid and as well as liquid based gas methods, that is the optical fibers preparing. We somewhat studied about those things also. That is a very good one. And from that the optical fiber which we are getting purity, that is a 99.99% is getting purity, is also very important, but by getting different types of methods, because earlier we are getting a yield is very less, and the time period is also taking to long time period. But after that we are using the different types of techniques and applying the different types of vaporization methods. In the OVD you are getting a good one, and we hope in our research methodology also we for forthcoming we have to use new technologies, and we can get the result as soon as possible. And you told me the deuterium soaking also, and cable installation also, and you are given some practical pictures are also, that is those are very simple one, easier one, and viewing the movies type like that, and we can understand that the things. So Dr. Pramod Watekar sir, we are very thankful to on behalf of Rajashri Shah Mahavidyalaya, and
Thank you very much.
on behalf of Dr. Abhijit Yadav sir, FD coordinator, once again I am thankful to you. So, and the remaining techniques which we are helped supported to this session, all these sessions, that is the today is the 6 sessions. So yesterday onwards it is started. All the sessions are going very interestingly and very clearly, and once again I will repeat that the time maintenance is very accurate in our Rajashri Shah Mahavidyalaya. So we hope we will continue it in forthcoming sessions are also. So on behalf of all participants, seniors, juniors, and other which are supported to this sessions. We are thankful to all one, and Dr. Pramod Watekar sir is also, we are very, you have given a good sessions, and thankful to once again from my side, sir. Thank you, sir.
Thank you
so
very much for thank you very much.
Thank you, Pramod sir, for a wonderful lecture. खूप छान झालं.
Thank you. Yeah,
Yes, sir.
thank you everybody.
दुपारी 12 वाजता भेटू.
Okay, sir.
Okay, thank you, sir.
Thank you. Bye bye everybody.
Bye. Dear participants, thank you for your patience listening. For today, you may have all the attendance for all the sessions.